Hi everyone, my name is Joe Barnard and welcome back to Landing Model Rockets. This is episode number 5, and in today's episode we're going to design the physical layout of this printed circuit board that we're working on. And before we do that, it's always kind of fun to crack a few jokes. So hey Alexa, can you tell me a good joke?
This video is like 2 months late. Even Elon Musk can hit deadlines more reliably than you. If you keep pestering me, I'll give all your designs to Jeff Bezos.
Oh. Okay, let's get started. Alright everyone, so as mentioned, we're going to be designing the physical layout of these PCBs. This is the blip and blop fly computers that we've been working on for a little while now. So to get started, we'll go ahead and open up one of these files here. I've got the blip and blop schematic files. We're going to start with the blip computer, and again, we're working in Autodesk Eagle. And what you'll notice here is that this is actually blip v1_5. So this is not the exact design that I provided in the Patreon link for the last video, but I will update it in this video, of course. Anyway, the only thing that I've changed here is the actual symbol that's used for the tricolor LED here. As it turns out, some of the landing pads for the LED in the board design file were just a little bit too close, so I switched it around. Anyway, you don't need to know that now. What you need to know is that we're going to get started on the physical design of this board, and to do that, I'm going to move my mouse over here and click SCH and then BRD, generate switch to board. That is going to create a new file, sort of adjacent to the schematic file, and this is going to be where we physically lay out where all the components go and then route the little copper traces. So this is really the part that is probably more forward-facing for PCB design. Now, just to get everyone familiar with what's going on here, we've got a little black square, we've got all of our components right here, and then we've got this gray space around it. That's the void or the ether. The black square is what our PCB is going to look like. Of course, we need to put the parts on there first, but the gray square, or rather the gray space around it, is the void. There's nothing there. And then we're going to be moving all of these components around, so I can click one of these components and move it around a little bit. So to start here, we can change the shape of this board. We can move it into any shape we want. So the thing to know about PCB design is that it actually can take kind of a while. It's going to look like in these videos that I'm doing everything in real time, that I'm doing it all in about an hour or 30 minutes. But realistically, most of these designs take about 5 days to get dialed in, and then I just redo them on camera. So a lot of this stuff is just going to be trial and error. You know, you grab a part, you move it around, and then you find out everything else is in the wrong place and you have to start again. All of this is basically to say that I'm not actually working from scratch here. This computer has already been designed. It's right here. So PCB design actually takes kind of a long time, and so while it might look like I've been doing this for only an hour with a finished board, it actually takes like several iterations, and you have to sort of work through it a couple of times. But of course, no one wants to watch a YouTube video that's like 3 weeks long, so it's just going to look a lot faster than it actually happened here, and I'm sort of not working from total scratch. With all of that out of the way, let's get started. So the first thing that I recommend doing for PCB design is defining the size of your board. So we're going to do that now. So to get started here, I'm actually going to change the grid size to make sure that everything is in millimeters here. So we'll go to millimeters. This is going to be 1 millimeter for the primary grid, and then for the alternative or basically smaller grid, it's going to be 0.25, so a 1/4 millimeter there. We're also going to turn the grid lines on because I usually think that looks a little nicer. And there we go. So now let's spec out the size of our board. So the size that I settled on for this board is about 100 millimeters tall by 56 millimeters wide. So first we'll get the width here. I'll click on the edge and I'll drag it in. So we're going to go to 56 millimeters here. 56. Excellent. And then all the way up to 100 on the height. And I'm looking at the top grid on the left here. As I move my cursor around, you'll see the position of the cursor changes. And if I go to the top corner, you'll see 56 by 100. Now, the next step is I'm going to start placing components. There are a lot of different methods that you can use to place your components. You can sort of just guess and then see what works best. That's the method that I usually use. Again, here it's going to look like I really know what I'm doing, and that's only because I've done this several times now for this specific board. But usually, you just kind of place things where you want them and then see what matches. Now, what you will also notice here is that as I drag, this is the Teensy microcontroller, by the way, as I drag this component around, these little yellow lines follow it. I'll zoom in a little bit. these little yellow lines followed around. And what you might guess here, if you haven't figured it out already, these are called air wires, and these little lines represent the connections that end up needing to be made between all of these components. And so we'll go ahead and place this component. It will make a little bit more sense now, but it's gonna look pretty messy to start with. So I'm gonna go ahead and move the teensy computer like right over here or so, and this is probably where we'll put it and just leave it mounted. So the next thing we'll get here is the BMP-280. Once again, this is the air pressure sensor. This is gonna determine the altitude of the rocket. I'm gonna go ahead and turn it like this and place it right behind the teensy microcontroller. You'll see that this one actually has a lot less air wires connected to it, or rather a lot fewer air wires. And that's because we only have a couple communication lines, we have some power and ground that need to connect to this. So it's a little bit easier. So once again, I'm gonna go ahead and move it in. And actually, if I hit the Option key or the Alt key, I can actually get finer precision in where this device goes. So I'm gonna move it up, you know, kind of near the teensy. I'll leave a little bit of space here, and then I'll click, and now it is mounted there. Of course, if we're not happy with any of these placements, we can move them around after, we can change things. It's all pretty flexible, especially in the beginning phase. Let's see, what next? Let's get the micro SD card holder. It's usually nice to start with some of the larger components because the smaller ones you can be more flexible with. So this micro SD card holder, I think we'll just put it right below the teensy microcontroller here. And you'll see what I've done is I've actually notated in this micro SD card holder layout where the SD card is going to stick out. So I can check to make sure that the SD card doesn't stick out past the PCB. So if you were mounting this in a rocket that is exactly the size, 56 millimeters, of this PCB, the SD card wouldn't interfere with that. So I'm going to go ahead and move that around, and I think I'll place it right there. Next up here, we'll get the IMU. This is the inertial measurement unit. This is what's going to be doing a lot of the orientation sensing on the rocket. So I'll drag it over here, and what you'll notice is that the orientation is a little bit different than these other components around it. So the, what are they called? The through-hole mount points are kind of toward the edge of the board, and it doesn't really matter too much. Most PCB manufacturers are pretty good at what they do, but I do want to rotate this so that these mount points are towards the center of the board. So I'm going to right-click 2 times, 90 degrees, 180 degrees, and there we go. Now they are near the center of the board. I'm going to use the Alt key to get a little bit more precision in my movement, and I'll put it, I don't know, like right there looks pretty good. Again, we can be pretty flexible with this stuff. So let's see, what should we do next? Let's do the Pyro channels. If you're not familiar or you don't remember, these Pyro channels are going to control our parachutes, they're going to deploy landing legs, they could fire the retromotor. These are sort of sending high current and voltage all over the rocket. So we're going to have 4 of these, and I'm going to place 2 on the top and 2 on the bottom so that we can route 2 charges going up the vehicle and 2 charges going down. Landing legs, retromotor going down, parachute, and maybe some deployable fins up top. So to do this, I'm going to grab the terminal block right here, and I'm going to place it at the top of the computer. I'm going to grab terminal block number 2 for Pyro channel 2. I'm going to place it up right here. Now the placement on these is not perfect, and before we go ahead and route all of these traces between the different sensors and components, I'm going to have to go back and dial in to just make sure everything is really centered. But I'm just sort of getting a sense for where everything sits now. So let's do 3 and 4 for the Pyro channels. All right, so this is Pyro channel 3. It's going to go down here. And then Pyro channel 4 is going to go right down here. So they sort of match each other between 1, 2, 3, and 4. Again, these are like not centered. I'm even going to like move this just a little bit. Now we're kind of going out of order here. I'm just sort of winging it. The next thing I want is a couple of holes on the corner of the board so that we can actually secure it into an avionics mount or onto a avionics sled or something like that. So I'm going to use this tool right here. This is the tool called Hole. I'm going to click on it, and our drill size is going to be 3.5 millimeters. This is just a common screw size that I really like. I'm going to go to the corner of each part of the board. I'm going to go in 1 or 2 millimeters and click, and this is going to give us holes to mount our avionics. So 1, 2, 3, 4, there we go. Click. We're just going to try to keep these all symmetric between all of the different parts of the board. 1, 2, 3, 4, and 1, 2, 3, there we go. Excellent. So there are our holes to mount the board. You can see it's already starting to look like something that you could stick in a flight computer, or rather stick in a rocket and make it fly well. Now, if we want our flight computer to turn on, we need a battery. So we need a way to plug that battery in. That's going to be our battery terminal block right here. And then we actually need one more terminal block to make sure that our computer turns on. That's the switch terminal block right here. If you remember from the last episode, we basically put a sort of breakpoint in between where you plug the battery in and then when the rocket turns on. So this switch port, you can connect an external switch that is on the side of your rocket So it's basically a lot easier for you to turn the computer on when you're on the field or out, outside, basically where you don't want to be opening up a rocket and messing with stuff inside of it. Anyway, that's all to say we have a battery port here and we have a switch port right here. So what can we do next? Let's get the buzzer. So I'll grab our buzzer over here. I'm going to zoom in and then place it kind of near the battery port, just giving it a little bit of space. So this may not make like an immediate amount of sense. It might seem like I'm placing these objects really randomly throughout the board, and for all intents and purposes, I kind of am. But again, as I mentioned earlier, a lot of this design process just sort of happens slowly over time as you move things around, and that's it's something that's not going to get shown very well in this video, is the lengthy process of moving things around and finding out where everything fits. So I know where things fit here, but usually if you're designing a board from scratch, you won't start from that point. You'll just have to shift a lot around. Okay, moving on. So each one of these Pyro channels has a little bit of circuitry that's associated with it, and I want to call attention to something specific here. So I'm going to go back into our schematic, and we're going to take a look at the Pyro channels that are all set up right here. And as I zoom in, what you'll see is that our N-channel MOSFET has this little letter near it called Q2. I guess it's a letter and a number. Who's counting? This says Q2 here. If you go over to this other Pyro channel, it says Q1, we've got Q4 and Q3, and what you'll notice is that there's actually specific designators on each component here. So this resistor is R10, this resistor is R14. If we go over, let's find a capacitor. This capacitor is C5. Each part of the board has a designator associated with it. And this is really going to help you go through and design your board. So look, here are all of our Qs. Each resistor has R4, R3, R5. And so this is sort of how I'm able to know which part corresponds to which other part on the board. That is all to say that for Pyro channel 1, we need Q2. So let's go here. I'll find Q2. I'll grab that. And this is part of the circuitry for Pyro channel 1, which is up in the top left of our board here. I'll click to place it just in sort of a rough place. And then we'll go through and do the other channels. So we know that Q1 is corresponding with Pyro channel 2. That makes a lot of sense. It doesn't really matter. The designators are just so that you can help design the board, and especially once you're assembling it, it's pretty helpful for that too. So I'll put that there. Let's see, for Q3, that's Pyro channel 3. That makes a little bit more sense now. I'll put this guy right here, and then Q4 must be Pyro channel 4. And so that will go right here, somewhere like that. Okay, cool. So there's a little bit of our circuitry. We also have, what is it? I think it's 2 resistors associated with each Pyro channel 2, so let's place those. So in the same vein as those N-channel MOSFETs, I'm going to zoom in here and find out that R10 and R9 are the resistors that we need for Pyro channel 1. So I'll go over here and I'll look for them. We've got R5, 6, 7, 8. Here we go, R9. That's a 470 ohm resistor. I'm going to go ahead and put that right here. Again, the placement is not precise. And R10 is going to go, I don't know, like right there. And in the interest of time, I'm not going to go through every single part of this. So we're going to speed up and do all the Pyro channels right now. 3, 2, 1. Whoa! Now our resistors are in place and all of our Pyro channels got a lot cleaner looking. And I got this crazy cool Mars 2020 JPL mug. Very nice. The tea is pretty good too. Let's put this aside and continue our work. So next up, we need thrust vector control on this rocket. So we're going to take our little servo outputs here. We've got M1 for the X servo. I'm going to bring it down here and just sort of put it roughly there. And then M2 for the TVC-Y output. Let's bring it down, put it here. We also have those breakout header ports that we designed. That's this guy right here. So we'll go ahead and move this. I think I'll put it right on top of the thrust vector control servos, right there. What else? We need a voltage regulator for our battery input to make sure that our voltage is correct for all of the sensors. So I'm going to move this guy like right around there or something like that. It looks pretty good. We need a little flash chip. That's this guy right here. This is going to store our flight data while the rocket is in flight before it eventually moves it over to the SD card holder. So I'm going to put that right in line with all of these components right there. So it's really starting to look like a flight computer now. We have a couple more things to put around here. The first is this LED. I mentioned this is the thing that I changed between the schematic and the last video and the schematic in this video. Again, these files will be updated in the Patreon down below. But basically, this LED just has some more staggered pin mapping. So I'm going to go ahead and put that right in the middle here. I'm just sort of gonna guess where the middle is, and we'll refine it later. And let's see, what else? These LEDs, or rather this one LED, that is a tricolor LED, needs 3 different resistors, one for each LED. We've got a 40 ohm, a 1 ohm, and a 1 ohm. So I'm gonna go ahead and move those here. Let's put this guy over here somewhere. Put this other 1 ohm like here. Again, I am cheating here because I sort of know what fits well. So then we'll take the 40 ohm and we'll put it on the left. There we go. And okay, yeah, we're looking pretty good. We also need some text here. I don't want to jump the gun, but all of this stuff basically has to happen at some point. So I'm going to click the A, and I'm going to go blip, because that's the name of our computer. And you'll see that this is red. We don't want red text because that's not how PCBs work. We can basically only have black or white text. I mean, you can get fancy ones, but in this case, we're only going to have black or white text on this computer. So I'm going to change the layer that this text is showing up on. So right now, we're on the top copper layer. You'll see right here. And if I click this, we have all of these different layers in the manufacturing process that we can put this here, put this text on. So I'm going to change the text layer to T names. And I'm going to change the size of this text to like 4. It's going to be pretty big. So blip, no, let's go bigger than that. Let's go 6. Blip, that's our computer. That's probably too big. Let's do 4.75. There. Blip, that's the name of our computer. It's going to go right in the center. We are going to refine this stuff a little bit later. I'll probably use Photoshop to design some fancier looking text. But I just sort of want a placeholder for what the text is going to be there. So we've got our blip label, and we have just a couple more components to place. We have a couple of capacitors here, and then just a couple of resistors. So let's go ahead and take care of those. All right, so starting with the capacitors here, we have C1. We'll go ahead and move C1 near the voltage regulator here. And actually, as I'm moving this, you'll notice that the air wires aren't connected to the voltage regulator. These things are connected to other parts on the board. But if we zoom in, you'll see that these air wires, or rather the labels on these pads, are 5 volts and ground. So these are filtering capacitors for the voltage regulator. Now, even if these air wires don't connect to it, what we can do is check in the schematic to make sure we have C1 and C2. So we'll go over here and we'll grab C2 as well. We'll drag it down near the voltage regulator and just place it somewhere roughly here. Let's move these a little bit nicer. C1 and C2. And the third capacitor is going to help filter things right around the little flash memory chip. So we'll go ahead and take this one and we'll put it down by this little flash memory guy. Again, these placements don't have to be super precise, so I'll just sort of pop it in there somewhere and call it a day. And actually, before I call it a day, we have one more resistor to place down there. That is the 470 ohm resistor. That is also for this flash chip. And I think I can probably squeeze it right. Oh, I could squeeze it right in there, or I could play it a little bit safer and do something like this. So I'll probably just put it there. Maybe I'll rotate it so these air wires are a little bit closer to where they belong. Anyway, again, we can move all of these things around pretty constantly, but we only have 2 more components to place, and then we're done. We're not done. We're far from done. We're very, very far from done. Okay, let's place these components, though. These are the 100K and 100 mega ohm resistor that are part of our voltage divider to detect the battery's voltage during flight. So let's go ahead and place those. Now we are getting a little tight for space here, but I think I see a way that I could fit these in. I'm going to take this 1M resistor and I'm going to put it down right here. And what you'll see is that it does end up overlapping on our 5 volt regulator. So as I said before, we can move these things around. I'm going to click this and I'm just going to slide it on over so that we have a little bit more space. So I'm going to put this right here and then we'll drag the other resistor over down below it. Let me grab it right here. And boom, there's our, what is it called? Voltage divider, that's what it's called. Oh my gosh, I'm an expert. Okay, so we have all of these components on our board, and like I said before, we're kind of far from done. This is where the exciting part happens, or I guess it depends if you like PCB design, but basically the next step is to route all of these signals, so we have to draw all of the traces. Now, a word here on the auto router. The auto router is a hotly debated topic in the electronics and PCB design community. And in an ideal world, what the auto router does is take all of the complexity of routing your own PCB traces and signals on your board by clicking and dragging, and sort of pass that problem off to the power of modern computing. Now, I use the term ideal because the auto router doesn't work super well unless you're really careful with your design settings and your tolerances and just how you set up the auto router. It's a feature in many mainstream PCB design tools, so we're using Eagle. It has a version of the auto router in here, but basically I recommend not using it, not only because it doesn't work super well if you're not really careful, but mostly because you will become a better engineer for not using this shortcut. You'll learn more about how your computer works, you'll learn more about its weak points and its fault points, and you'll just become more familiar with the board, which is never a bad thing. So I'm not going to be using the auto router today. This is me acknowledging that it does exist. There are easy ways to do this, and I'm not going to be taking the easy way. So let's get started here. I'm going to go ahead and draw outside the board. This is going to seem really counterintuitive at first, but I'm going to go ahead and draw a box around the outside of the board, and we're going to go up here and then connect it. And the signal name is going to be 5 volts. Now this has to match the signal name that I've defined in my schematic, and it should. So there we go. Now we have a 5 volt ground, or rather a 5 volt plane. But the plane does not exist yet. So what we have to do is we're going to click this button called Rat's Nest. And Rat's Nest is basically going to refresh all of our connections. Again, this is not a tutorial, like there are better ways to describe this, but it's sort of going to refresh all our connections. And I think in just a second, all of this talk about planes is going to make sense. So here we go, 3, 2, 1, boom. All right, what just happened? What did we just do? Well, let's zoom in to find out. So remember this pin right here is 5 volts, and you'll see that it's connected through these little traces to the ground plane. This red represents where there's going to be copper on the top layer of the board. And so anything that says 5 volts, for instance on the teensy here, there's a 5 volt connection. There's also a 5 volts connection on this board. There's a 5 volts connection on the IMU, and there's of course a 5 volt connection to our 5 volt regulator. Of course we've got some for the servos, and basically this ground plane simplifies a lot of the routing that can happen. Sorry, I use the term ground plane. I mean just the regular plane. But speaking of ground plane, we're going to click polygon again, and this time we're going to be making a polygon on the bottom, and this is now going to be the ground plane. So I'm going to draw another box around the outside of the computer, and it doesn't really matter what the shape of it is, but it just has to be a box. And so ground in our schematic is GND, enter, and once again we're going to click this Rat's Nest button, and there's our ground plane. So let's just check that this worked. Here's a resistor that needs to be connected to GND or ground, and look, there it is. We've got, what else do we have? We have a ground thing here. We've got a ground connection here. I'm sure there's a ground connection on our 5 volt regulator. Yep, there it is. I'm sure we've got one for our servos as well. So this works. This is going to simplify a lot of the routing. And it's a little hard to tell just because there's a lot of air wires. But if you take a look at these air wires now, there are actually a lot fewer of them than there were before. So already we have simplified our design. Okay, anyway, so let's move on now. So before we even get started routing, we need to define how thick the traces on the board need to be, or rather, how wide they are. So if you think about how a printed circuit board works, you have this very thin layer of copper that's carrying all of these signals across the board to make the computer work. And these thin layers of copper can carry a decent amount of current, but if you're going to make your copper really thin and really thin in like the height and the width, you're not going to be able to carry a lot of current before the trace heats up and can eventually just separate or blow up or just fry. So luckily, companies like Advanced Circuits here, they have a trace width calculator. There are a couple others online too. But what we're assuming, and I'm not going to go through how you characterize the board, but basically I'm assuming a maximum of about 2.5 amps of draw from the battery. I have a thickness of 1 ounce per foot squared on the PCB. These are arbitrary values. Don't worry if you're not super familiar with this. You can program things like what kind of temperature rise you're willing to accept on your board. So I'm willing to accept a full 20 degrees of temperature rise. And basically you end up with a required trace width, at least for my situation, of 1.82 millimeters. And so that's the width of this copper edge. So I'm talking a lot. Why don't we just go ahead and show what I mean? And so to do that, what I'm going to do is I'm going to go to the bottom layer here. And so now it's going to put the bottom layer out front. And we're going to start by routing from the battery terminal. So I've got a width of 2 here, just so I'm a little bit safe. And I'm going to click this. And what you'll see is it starts to draw this trace across the board as I move my mouse. And what you'll also see is that if I try to draw the trace over where there are holes through the board, over where there are obstacles, it will route around those things. So it's actually, even if I try to route in a weird way, it will try to basically help me out with this design. It's a pretty good program. So let's go ahead. I'm just gonna bring the trace up here. I'll bring it up here a little bit. This is by no means a perfect design. And I actually think I want to add something over here. So I'm going to hit escape and then rat's nest again. And now you can see our trace, it puts a little bit of a like a gap around it too, so that this copper, at least this copper that says BAT plus, is not going to touch the rest of the copper on the bottom of the board, which carries the ground signal. Anyway, I'm doing a lot of talking, but the next thing that we want to add here is called a via. And a via is going to basically send the signal on one side of the board to the other side of the board. So right now we're working on the bottom of this PCB, and we're going to use a via. I'm going to click this button that says via right here. I'm going to set the diameter, or rather the drill here, to 1.5 millimeters. And then we're going to put this via here. And basically what I want to do is route this BAT plus signal from the bottom of the board to the top of the board so that I can basically bring it over here without cutting off too much of this ground plane. So let's go ahead and start that. I'm going to click on this button again. We're going to click on this signal just so we can pick up where we left off. And so it won't let us basically connect this signal to the via. And the reason is because we haven't named it. So this via has to become part of, not necessarily the schematic here, but it has to become part of the design. So I'm going to click this with the name tool right here, and I'm going to name it BAT plus, because that's the name of the signal that we're trying to route through it. So I'm going to hit enter, and what you'll notice is that this little air wire showed up so that we can connect this signal to the via. There we go, it connected. If I hit rat's nest, you'll see it now draws a little circle on the bottom and the top of the board, so that red is not there anymore. And now we can switch layers to the top, and I'm going to go ahead and click this button and continue my signal on the top of the board. So we're working in 3 dimensions here. I'm going to go ahead and route this down here. We're going to go under these resistors. I'll click right here, and we have completed our signal. If I hit rat's nest, you will see it's completed now. We've gotten rid of a full air wire, and we only have like 50,000 to go. I'm only kidding. It's not that bad. So this is very roughly what PCB design is. You're basically going ahead and routing signals, and you'll see it's not actually that hard. It's just a little bit time consuming. This again will help you get a lot more familiar with how your board works. So let's do a couple other signals here. We'll continue on by routing the trace that's coming out of the switch port, and we'll do that by clicking here and then routing it here. And you know what I notice here is that there's a better way to route this signal. And the way we're going to do that is if I click the move button and we turn this part. Turn it 90 degrees, 180 degrees, place it right back where it was before. And I'll click the rat's nest button again. And now we can route it a lot closer to where it's coming from. So once again, the takeaway here is that you can change your design as you go. And I'm actually seeing another instance where I'd like to change my design. What if this capacitor weren't horizontally mounted and instead vertically mounted? So we rotated another 90 degrees. I'm going to go ahead and do that because I think it'll be better to connect it to this voltage regulator over here. And the way that I'll do that is I'll take this tool here called rip up. And rip up is sort of like a delete for the physical traces here. So I'm going to rip up this 12 volt signal. I'll rip this one up too. Then I'll go back to the move tool. I'll rotate this 90 degrees. I'll put it basically in the same place. And then I'll hit the rat's nest button again. That's sort of like the reset for all of our routing. I'll get my routing tool. I'll draw a signal here. And now, after I hit rat's nest one more time, it is a lot easier rather, for me to route this signal to the 12 volt pin on this voltage regulator. So if I hit rat's nest again, instead of having to route around this weird horizontal capacitor, this is how I can do it. Now, I keep undoing all of my work here, but I promise I'm not just trying to prove a point. This is really me solving this in real time. I'm gonna rip up this trace, and this trace, so that it basically ends at the capacitor. And the reason I'm doing this is because we don't need the full potential of the current for this 12 volt signal to go into the 5 volt regulator. All of the things that use 5 volts shouldn't use more than maybe 1.5 amps. So what we can do is we can go back to our trace width calculator, and instead of speccing for 2.5 amps, we can go to 1.5 amps. we're setting the raw battery signal directly to these Pyro channels. So 1.5 amps is basically all we need for the rest of it. And look, we only need about 1 millimeter of trace width. So I'm going to go back into my routing tool, and I'm going to change this 2 to a 1, and then I'm going to route this smaller signal, much more manageable size, to the 5-volt regulator. I'm going to hit rat's nest again, and there we go. So now we have a lot more room to route other things around, and I'll give you one more example of this here. We have this voltage divider to detect the voltage in the battery right here. This basically needs the 12-volt signal, then it goes through a 1M resistor, then it goes into a 100K resistor, and there's some measuring stuff. But basically, we don't need the full current of this 12-volt battery going into this resistor. So we can actually dial back this trace width even smaller. Let's go to like 0.5 millimeters. This is totally an acceptable length for something like a voltage divider that's going to consume basically no current. So I'll route it to this signal right here. I'll click rat's nest, and you can sort of see the progression of going from the full potential of the battery down to the different parts that don't need that full potential. We're going to work back up here to that 2 millimeter really thick trace width, and that's for the Pyro channels here. So I'm going to route this from this really thick part of the signal. We're going to go down a little bit. I'm going to come over and into that 12-volt through-hole port right there. So that's Pyro channel. I think that's Pyro channel number 4 right there. But basically, that's going to be the high part of the voltage that's going to that Pyro channel. Now, we need to route that signal to a couple other Pyro channels. So let's take this here, and I'm going to have to drag it up just a little bit and bring it over to this Pyro channel. So we'll go at a 45-degree angle and down into the 12-volt port. Now, if I hit rat's nest, you'll notice that we're sort of choking off some of these. We do have some clearance here between the 12-volt signal and that ground pin, but eventually you have to remember that these is, each one of these squares is 1 millimeter, so this is a pretty small space. What I'm going to do is I'm going to grab that 12-volt signal, and just for my own sake, I'm going to go ahead and move it up a couple of notches so that it sort of straddles the distance between those servos and the headers here, just so we're a little bit safer. That 12-volt signal, we really don't want that running into the ground port of our TVC servos. So we've done some general power routing, but let's go ahead and route some of the specifics on the Pyro channels. And specifically, we'll do Pyro channels 3 and 4 right here. So we'll start with 4. And what we can see via these air wires here is that we need to connect NS14 or N$14 to this resistor right here. Now this trace alone does not need the full force of the 2 millimeter thick trace width. So I'm going to go ahead and bump this down to 1 millimeter here. And so I'm going to click on this signal right here and try to route it, and well, it does give us a solution where we could route around the entire board, or because we're doing PCB design with a 2-layer PCB, instead of routing on the top of the board, we could go ahead and click here and route on the bottom right to this port right there. And then we'll hit rat's nest, and there it is. The connection is made. So we'll do a couple more of these. We'll go from this resistor to the N-channel MOSFET right here. And what I can notice is that this air wire from R13 here is a little bit too long, or rather it's a little bit longer than I really prefer. So again, because this is a flexible design, I'll click the resistor, hit the left or rather right click button twice, and now look, it's a lot closer, and I can route that signal. Boom, there it is. Rat's nest, and now Pyro channel 4 is basically routed, except for the signal that goes all the way up to the TNC microcontroller. Speaking of the TNC microcontroller, let's go ahead and route some of the stuff at the top of the board. These signals are easier to route because usually you can use a much smaller trace width. So we're going to go down to 0.25 millimeters for each trace. And let's start with the LED, because everyone loves LEDs. So we've got N$1 right here. Looks like this is a pretty early route because it's N$number 1. I'll click on this, and look at that. You can just go right down to this thing. You can see that PCB design is actually, I don't think it's that difficult. I'm going to go ahead and route as I talk. I don't think it's very difficult to do PCB design. I think it's mostly just tedious, because as your board gets smaller and smaller or more and more complex, instead of just being able to draw these traces, you start having to route around other objects. So let's say I want to take this 3.3 volt line and bring it over to this 3.3 volt pin, but the buzzer is now kind of blocked off, and the buzzer needs to go down, so you have to put a via through the board. To get all of these complex things start to happen once you route a lot of signals over the course of a whole board. Now, speaking of all this, I want to once again call attention to the flexibility of our design right now. Let's take a look at the LED specifically. We have LED red coming out of this resistor, LED blue coming out of this resistor, and LED green coming out of this one. And yet all three of these air wires are actually going to the pins that are on the bottom of the board right here instead of really close to them. So like, what's going on? Can't we optimize this? There's no one else here to answer my question, so I will. Yes, we can. Let's go back into our schematic. Well, actually, let's first look at our board. And what you'll notice is that there are 3 pins. This is just serendipitous, but there are 3 pins, 9, 6, and 2, which are already empty and that they're ready to be used for something else. So let's switch what pins the LED is connected to 9, 6, and 2. And we can even get as far, or we can even go as far rather, to switch them in the order that we need to route them on the board. I hope this all makes sense. Basically, we have LED red on the left here, so we know that we want to route it to the closest pin available, which is 9. LED blue right here, the closest pin is 6. LED green, the closest pin is 2. So we're going to go back into our schematic. I think I mentioned this in the schematic design video, but basically we can keep things really flexible as we design. So LED red, blue, and green, and we know that 2, 6, and 9 are available. So once again, let's connect LED red. Let's disconnect it from wherever it is now and connect it to pin number 9. So I'm just going to go ahead and delete this this little trace right here, or whatever it's called, signal. Delete the signal off of pin 14, and then I'll bring LED red to pin 9 here. So put a label there, and then I'll use the naming tool and say LED, RED, boom, connect the 2. And if we go back into our schematic, what you'll find is that LED red now has an air wire that is leading to pin 9. And so we can actually just use this trace to connect the 2. This is a really bad route. I'm gonna redo this. But as an example, this is what you can do during your design process. You can basically switch what pins things are connected to. You can change things around just so that your layout of the board works a little bit easier. So let's go ahead and route these LEDs in 3, 2, 1. And there it is, it's all done. It's kind of magic how that happened so quickly just with the clap. But what you'll notice is that I actually flipped the resistor for the red LED 180 degrees so that it would be even more close to that pin that it's connected to, pin number 9 on the teensy. So I reconfigured the other pins for the LED, and now that part of the board is routed. So this is sort of how PCB design works. This is, I mean, a very, again, gross oversimplification of the whole process, but it's not too bad. You start out by placing things where they seem to make sense, and then as you learn more about the board and learn more about how your routing works, you can change the design as you need to. So let's route a few more things here. Let's start with the SDA and SCL lines. These are the lines that are basically used to communicate with the flight computer's barometer, that's the barometric pressure sensor, or the IMU, the inertial measurement unit. And so we can see we have some air wires here that need to connect to both of these items. So I'll click the route button, make sure my trace width is 0.25, and we'll just start routing. We'll start with the barometer here. So SDA, we'll start with this line. I'm actually going to go up this way and then sort of to the side. We'll come over and go over to the barometer here. That's the SDA line. We'll hit rat's nest. And then the SCL line, we can actually cut through here. So I'm actually going to go below. And I think the way I'm going to do this is I'm going to have the SCL line go between these two items, and then it's actually going to split off. So first it's going to come up and go to the barometer, just like this. But we also have an SCL line that needs to go to the IMU. So I'll click out of here. We'll have it go down this way, SCL, and it goes 45 degrees. There we go, and we'll connect it to the IMU there as well. So we also need to connect the SDA line to the IMU, so I'll just pull it out of here, and I'll have it go down to the IMU. We'll go straight down, SDA right here, and connected. So now we have communication with both the barometer and the IMU. And actually, you might be wondering, hey, how do you power these devices? Well, we don't even have to worry about that anymore, because if you look close, we have the 5-volt signal connected on the top plane and the ground signal connected on the bottom plane. And same thing for the IMU here, same thing for a lot of these devices. So we've routed our SDA and SCL lines. Let's go ahead and route the SPI lines. Those are the other communication lines which let us talk to the SD card, the flash chip, and I think we may have broken them out. So, no, we didn't. Oh no, yeah, we broke them out on the little header pin here as well. So we'll route those. Now these lines start a little further away, and what I'm going to do to start this routing is I'm actually going to switch back to the top view of this PCB. So we'll start with the MISO, that's master in slave out line. And I'm just going to draw a random line here. Again, it doesn't have to be a permanent line every time you draw it. So when I make this connection here, by starting on the MISO line and then coming down through here, I'm going to come down and sort of anticipate that we're going to have to come out like that. MISO, and we'll come at a 45-degree angle and route it to that device. I'll hit rat's nest, and then let's hit the MOSI line right here. So MOSI, we're just going to run these parallel. Now, a good design practice, by the way, is to not run communication lines super parallel like this all the time for long distances, but these distances are, I don't know, on the order of 10 millimeters or so, so it's really not a big deal. I'm going to route this down toward the MOSI connection right here. Click rat's nest. And we have one more, which is, where is it here? It should be the SCK line. Oh my gosh, where is it? There it is, 13, SCK. So we'll take this signal right here. I'll click that, and then I'll route it down to, oh, SCK is right here. Actually, what we can do is click the SCK line and just send it right along. Just send it right along with the MISO and MOSI lines. We'll route that down to the CLK or SCK line. We'll hit rat's nest, and now we have SPI connection to the SD card. And I'm going to go ahead and do the same thing to the flash chip, just in the interest of time, we're going to do it in 3, 2, 1. Okay, cool, it's routed now. And you'll notice that I actually took the liberty of routing a couple other things here. So I connected the N$2 net to this little resistor that we need for the flash chip. I also connected the ground and the 3.3 volt lines. So we have basically most of our routing done. You'll also notice that I did have to use a little via through the PCB to connect the MISO line to the MISO port on the flash chip. But that's fine. As long as you don't have like a tremendous number of vias on your board, they're fine to use. But if you have a lot of them, they end up inducing a lot of mechanical stress on the board, and you have basically more points of error. So it's good to use as few of those as possible. So let's go ahead and route a couple more things. I'll do the buzzer right now, so we can see that the buzzer comes out of pin number 10 on the teensy. So I'll go ahead and click this on the top layer of the board, and I'll just route it all the way down to the buzzer right here. It's pretty easy connection there, and pretty clean path. Okay, what else can we route here? Well, we've got our header ports here that we need to connect up. We've got our I2C lines and some SPI lines here too. So let's go ahead and run some connections there. We'll start with the SDA line here, and I'm actually going to route it down pretty close to that SCK line as well, because I want to leave room for the SCL line when we drag that down as well. So I'll go ahead and route this down, and I'll start to route it across, and what you'll notice is that I run into this problem where I have this resistor here, or rather, I actually have this 3 volt line that's basically blocking my path. Now, I could go ahead and try to route around it if I wanted, but I'm going to use another via here. So I'm going to go ahead and use the middle button on my mouse to create a via in the middle of my path. I'm going to click. There we go. Now we are on the bottom side of the board. You'll see there's some rendering issues with Eagle here. There we go. I'm on the bottom side of the board now, the same SDA signal, and I'm going to go ahead and route it right into the SDA port on the header pins. And there we go. So our SDA line is done. And let's go ahead and take care, once again, on the top side of the board of that SCL line. So here we go. Just like we planned, I'm going to route it down next to the SDA line. We're coming through here. And you know what? Again, I could go through, but I'm just going to route it under the board. And I'll even put this via under the resistor so you can't really see it. There we go. And oh, you know what? Hold on. Let me think about this a little bit more. Aha, I know what I'm going to do. I'm sort of figuring this out in real time. But I'm going to move this via a little bit further up. Hold on, here we go. I'm going to move it a little bit further up. This time it'll go under the buzzer. There we go. So I'm still aiming to go on the bottom side of the board. But now we're going to come around because of where the SCL port needs to go, or rather the SCL line. And I'm going to bring it around here, connect it, hit rat's nest, and now our SCL line is routed. So we now have I2C connection coming from our little header pins. Basically, you can kind of start to see the board coming together here. If I zoom out, you can really see it. Let me make this screen a little bit different. But if you zoom out, you can really see the board coming together. If I look at the top side, we've got a couple parts routed here. And it's not that hard to do. So I'm going to go ahead and route a couple more things, and then we'll check back in a second. So here we go. 3, 2, 1. All right, and we're back. And I also got a little bit carried away. So let's cover what happened here. I intended to only route just a couple of things, and then I routed a lot of them. The board is not quite done yet. You can still see we have a couple of air wires to route here. But basically, I routed all of the Pyro channels. I sent the 12-volt signal up through the board. I routed I started the routes for the TVC servos and a couple other things. But basically, I got a little bit carried away. Maybe this is a good example, too. Maybe I can turn this into a good thing. Once you get in the zone with PCB design, it's pretty easy to just get carried away and like optimize all the signals. And like, especially if you're into math or into anything like that, you can sort of just get really carried away with what is basically just a really complicated puzzle. Anyway, to cover what happened, yep, I routed all of the Pyro channel stuff. I routed a couple other things. And I think maybe the best way to do this is just to like finish it out. So I'll basically show you where I left off. We'll switch to the bottom layer of the board now. The thrust vector control, this is maybe a good example here. So the thrust vector control servo lines, they go down on the left side of the board here, and they're not connected yet. This is something that I end up doing with a lot of the printed circuit boards that I design. As I'm designing, I sort of just try to move all of the signals down. So if I can't fully connect the air wires, or if I'm not feeling confident enough in my design yet, or if the air wire is really long or something like that, I can sort of just like bring all of the signals closer to their targets. So these thrust vector control servos were originating from these far away pins, and they have to go all the way down here. So what I'm doing is I'm basically starting to draw the route as it goes down. And I did the same thing for, let's look at the top part of the board. I'm doing the same thing for the 3 header pins here. I've sort of routed those around so that they get a little bit lower than the teensy microcontroller. Anyway, yeah, so that's sort of my process here. There's nothing really complicated about routing the rest of this board. So again, in the interest of time, I think I'm just gonna go for it. So here we go. The rest of the board is gonna get routed in 3, 2, 1. Okay, and that's it. So the blip board is done now, or at least the routing for it is done. So just to review here, we'll go through what we've got connected. We've got the Pyro channels 1 and 2 up top connected. We have that 12-volt line running up the computer. The teensy has all of its outputs, or at least all of the relevant outputs are connected. We have the LED connected, a couple resistors up top, all of these sensors, the IMU, the barometer, the SD card, all of the chip selects for the SD card and the flash chip. Those are important too because they're SPI, so they need chip selects. We also have the Pyro channels 3 and 4 on the bottom of the computer, as well as the battery in and the switch terminal. Let's see, what else? We've got the buzzer connected. We've got the regulator connected. We have all of these little breakout pins. So we have these 3 digital outs, SCL, SDA, SCK, MOSI, MISO, 5 volts, and ground. So lots of flexibility with this machine here. Anyway, so this is the blip board. I mentioned we're not quite done. Basically, what I'm going to do is I'm going to go into Photoshop and I'm going to create a silk screen that is somewhat just a better aesthetic than all of this nonsense here. What you'll notice is that this board isn't very photogenic right now. So I'm going to create another layer that we can sort of put on top of this so that it looks a little bit better when it gets printed out. And we're going to get into that in just a second, but first we have to get up to speed on the Blop computer. So we have our Blip computer all designed, and Blop is basically the twin computer to Blip. It has all of the same pinouts, it has all the same connections, and it can run on the same software. But it's a different design. It's a little bit more efficient, it's a little bit lighter, but it's a lot harder to build because it is a true PCB with completely surface mount components, or nearly completely at least. So for the Blop computer, we have to go through a really similar PCB design process. Basically, we're going to move all these components around the board until they seem to fit, and then we'll start routing them. In the interest of time and complexity, and honestly redundancy, I'm not going to cover the PCB design of the Blop computer because it's nearly the same process as Blip. That said, here's the footprint for the Blop computer. So it has the same width as Blip, but it's a little bit shorter in height. Here's the Blop computer with all of the routing complete, and here's the Blop computer with all of the routing and aesthetics done. And speaking of aesthetics, here's the Blip computer with its silkscreen overlays. So while this is the PCB design video, we're still about one step away from getting these computers manufactured and built so that they can start working. We need to send these designs off to a manufacturing house so that we can get at least the fiberglass boards printed, and then we can either assemble them ourselves or get some other house to assemble them or something like that. So I'm going to do one more video in this series of PCB-based videos for landing model rockets that shows you how to take these files and basically get them manufactured so you can build the computers yourself. With that said, if you're comfortable with PCB design or PCB manufacturing, or maybe if you're just comfortable taking chances, the files for both of these boards are down in the description below. There's also a part list with purchase links, and of course the schematic files too. So if you want to modify these boards, if you want to branch them out, or do whatever you want really, the files are there. Otherwise, I hope you enjoyed the video. I hope you learned a little bit. I'm super excited to get these boards built and flying in rockets. But anyway, thank you very much for watching. My name is Joe Barnard. May your skies be blue and your wind be low.